Hi students, so Mr. Clucky here. I'm going to go ahead and try to explain and teach you guys our task or our activity during task 2. So on our HyperDoc here, we're at task 2 now. We're building our consensus models. You guys, it sounds like what we're going to do is we're going to click this link here, which is, if you clicked it correctly, you should be listening to this Edpuzzle video. And I'm going to talk through our consensus model just so that you guys can understand it. And then when the video is over, you're going to want to make sure you copy this consensus model into your notebook if you haven't done so already. So either this consensus model is already copied into our notebook. If it is, it should be in our progress tracker on that 2-page spread. Otherwise, after you finish watching this video, make sure that you copy in the consensus model now that I have explained it. So I'm going to go ahead and go to our consensus model here. And I'm going to go ahead and zoom in. And I want to explain what we've kind of drawn in. So this is what our progress tracker should look like when we're all finished up. And I want to explain some of the main parts here. So at the very top of this, we are listing our question. Okay, so our question so far in class has been, how can we use magnetic fields to explain the interactions at a distance between the magnet and the coil? That's what we're really focusing in on, is how can we explain those interactions between the magnet and the coil? All right. Now, next to that, we have where we're going to gather evidence. So to answer that question, a few sources that we can look at are going to be our experiments in lesson 2, where we use the magnets and the electromagnet. We can also use our iron filings demonstration. That was from lesson 5 or lesson 4, I believe. We can use our computer interactive with a magnetic field from lesson 4 and lesson 5. And we can also use our compass investigations from lesson 4. So you'll notice, to answer this question over here about how does the magnet and electromagnet interact, right, the magnet and the coil, we're going to get our evidence from these investigations that we've done throughout the first 6 lessons. Okay. And now down below that, notice I've written, we're going to explain these things that we found out with sources of evidence using words and pictures. And you guys attempted to do this already the day previous. All right. So thinking about the day before, we made our cause effect table. And then you guys practice modeling some of these things into our notebooks, all right, trying to explain our magnet and coil interactions. Sorry, I have a fly that was flying around. We attempted to do that. Well, now I'm going to show you how I explained it. So we're going to go ahead and copy this into our own notebooks now. And this will become something that we can use to review for our upcoming assessment, as it might be extremely important to know how to represent our coil and magnet system, or those magnet interactions. So the first area that I want to focus on is right here. And this is our starting system. I'm going to underline this here. This is our starting system in the speaker before it's plugged in. So I thought it was important for us to show, what does the speaker look like using magnetic fields before it's plugged in? Okay. So now that I've underlined that here, let's go ahead and show what that looks like. So before we plug our speaker in, you'll notice that we've got a magnet right over here, and we've got our coil of wire. Okay. Now, if we draw our magnetic fields, because the coil of wire is not plugged in yet, it does not have a magnetic field. So it is not exerting, there is no magnetic field around it, which means there's no magnetic field lines coming out from this image, and therefore it has no force of attraction or repulsion, which is why we're not seeing any magnetic fields. Now, that is different for our magnet, because notice, does our magnet always have a magnetic field? Yes. We can't turn our permanent magnets on or off. So that's why we see that we've got magnetic field lines coming out, drawn here. Notice our magnetic field lines are coming out of the north side of our magnet, and they're curving up to try to get to our which side, right? And that would be the south pole of our magnet, all right? And I've represented that with our triangles, but I'm also drawing on here with arrows to show that, hey, our magnetic field is only existing in our permanent magnet. It's coming out from the north pole and into the south pole. Right. So again, this is our magnet system, all right, the speaker system before it's been plugged into a music player, before we plugged it into that energy source. Okay. Now, explaining it in terms of cause and effect, I've got it over here. So I said our cause was that the coil gets connected to the battery. The effect is that there are forces between the magnets, all right, and this is because the coil has a magnetic field now too. So as we investigate our systems, as we do this, we need to see and draw some new pictures. Okay, so our cause is we are now going to plug it into the battery. there's going to be forces now with the electromagnet. All right, there's going to be forces now between the magnets, and the coil has a magnetic field now too. Okay. As we do this, I want to go ahead and take note to show you our key over here. So you'll notice our key right now. The blue arrow is always going to show the force from our magnet on the coil. And the red arrow is going to show the force from our coil on the magnet. And then you'll notice I haven't drawn it in here, but in here is where we're going to see these triangles that look like this. And those triangles are going to represent our magnetic field. I guess I can move my face there. These triangles that we see are going to be the magnetic field. So let's go ahead and investigate the two situations we've got going on here. All right, so let's go ahead and look at our two system interaction here of when we do that. Now, I'm going to go ahead and zoom back out. So when we plug our magnet and our coil of wire together, we could have two scenarios. So here is scenario number one. I'm going to zoom out so we can see. You'll notice that here we've got our battery. It is plugged into our coil of wire, and we've got some forces, which I've drawn with these arrows. So again, this blue arrow is showing us the force from our magnet on the coil, and this pink arrow is showing our force from the coil onto the magnet. And as you can see, these two objects are repelling each other. All right, we can also notice they're repelling each other because we've got the north side here and the north side of this magnet here, which means that they're going to be repelling. But we're also seeing these magnetic field lines that we also saw in our simulation online interactive doing some pretty weird things. So notice the magnetic field lines are coming out of our two north poles, and notice they're not interacting with each other. Okay, they're forming this kind of dotted line between where they're kind of separating. Okay, so they're pushing away, and we're seeing that in our magnetic field lines. We're also seeing it in our force arrows, right? They're not pulling at each other, not doing anything like that, but they're pushing each other away. Okay, all right. So that is our first scenario when we plug in the electromagnet to our battery, or plug in the coiled wire to our battery. And just go ahead and talking about the cause and effect and the why of that will be over here. So our cause was we flipped the magnets so that similar poles form, or that similar poles face each other. Now this could have been south and south. I just chose it to be north and north because they do the same thing. They should both repel. So the effect is that the force pairs between the magnets become repulsive, right? We're seeing these arrows showing that force of repulsion, and they're repelling because the magnetic field has changed. And our magnetic field has changed and is now shaped like this, where we've got our north pole magnetic fields are going out towards each other, and then they're meeting each other and pushing away, trying to get back to the south pole, which results in that force of repulsion. All right, now, conversely, the other situation we could have had was over here. And I'm going to move my video up here so we can see. So notice in this situation, we have our battery. And now instead of it being that similar poles are facing each other, we now have opposite poles. So our opposite poles. So our cause here is now that we flip the magnet so that opposite poles are facing each other. We've got a north and a south. And as you can see in this situation, we now have a force of attraction. You can see that the magnet is pulling on the coil of wire represented by this blue arrow, and the coil of wire is now pulling on the magnet represented by this pink arrow. And we're seeing that force of attraction. All right, so our effect again is the force pairs between the magnets become attractive. They're pulling. Now, I want to draw in and bring attention for the why to because. So why are we seeing them attract? Well, again, when we look at the magnetic field lines, what are they doing? And we saw this in our interactive yesterday as well. But notice that the magnetic field lines from the north pole of our permanent magnet are now going from this north pole to which south pole? And that would be the south pole of our electromagnet. So notice our magnetic field lines are moving over here to this other south pole. And not all of them, right? Some of them are curving to go to the other side. All right, like this. But some of those magnetic field lines are going straight across to this south pole right here. And when they do that, that results in them pulling that object in there and getting that force of attraction. Okay. So again, these are attracting because our magnetic field has now changed. And we're seeing all of these magnetic field lines going from the north pole of our permanent magnet or of the disk magnet going over to the south pole of our electromagnet, which is now resulting in that force of attraction. All right. So here is the overall picture of it. Remember, I have a picture of this posted on PowerSchool, or not PowerSchool, on the Google HyperDoc. You will need to copy this in to your notebook, all right? And then this can also be another tool to study as you prepare for the assessment. So we should be able to give a cause, an effect, and then be able to explain why we're seeing that effect in all these situations. All right.